In this footage, we see the damage inflicted on the German Leuna synthetic fuel plant by strategic bombing. In May 1944, bomb target priority shifted from destroying the German Air Force and supporting the D-Day invasion to targeting German oil production facilities. Leuna Works was Germany's second largest producer of synthetic fuel. From May 12, 1944 to April 4, 1945, the USAAF and RAF sent over 6,600 heavy bombers to attack the 757-acre complex. That's 5 times the number of bombers sent to attack Dresden in February 1945. A USAAF miscalculation caused the 8th Air Force to send bombers to attack such a small target over and over again. A total of 128 heavy bombers were lost in the 22 Leuna plant bombing missions. The intent of this video is to focus on why bomb strike accuracy was so low and why the small percentage of USAAF bombs that did contact the plant caused superficial and ineffective damage, while RAF bombs were very effective, and the lessons learned in the attack. We will use period maps, historical archive documents and footage, and RAF and USAAF post-war evaluations of the attack in developing the video narration. As discussed in this channel's video, the Reich's Achilles heel was oil. The commander of the German Air Force stated the raids of Allied air fleets on Germany's fuel supply installations were the most important combined factors which brought about the collapse of Germany. The principal source of Germany's aviation fuel was from the hydrogenation process, as shown on this chart representing sources of Germany's aviation fuel from a 1945 United States Strategic Bombing Survey report on German oil. The hydrogenation process turns coal into synthetic aviation fuel. This table lists the hydrogenation plants processing Germany's synthetic aviation fuel from a 1945 British Bombing Survey document. By April 1944, the Leuna plant was Germany's second largest supplier of synthetic products at 51,000 tons. This image shows a location of Germany's synthetic oil plants from a 1996 Air Force History Program document on USAAF operations and military intelligence in World War II. Berlin is here. The Leuna plant is here. The plant is within the 600-mile bombing range arc of the 8th Air Force. A view of the plant prior to bombing from a 1947 United States Strategic Bombing Survey report summarizing the Leuna bombing attacks. The plant prior to the bombing attacks. Another view of the plant with the caption that bomber crews used the 13 chimneys to help identify the target. The plant's boundary is in this shaded area. The plant is 2.2 miles long, 0.66 miles wide, and occupies 757 acres. The plant's waterworks is here. As of April 1944, the plant consumed between 150 to 180,000 gallons of water per minute and was powered by 924 miles of cable lines. Another image of the Leuna plant with its 13 chimneys. German posters of the Leuna plant. The principal goal of attacking Leuna was to deprive Germany of its synthetic oil products. If the plant's production stops, this goal is met. This table summarizes the 22 bombing attacks. The columns include the mission attack number from 1 to 22, date of the attack from May 1944 to April 1945. Attack force is either 8th Air Force or RAF. Target sighting method used. Number of bombs dropped. Bombs striking within the plant zone. And percentage of bombs striking within the plant's fence boundary. Out of the 85,412 bombs dropped, 8,643 struck within the plant's boundary, or 10.1%. This is considered a low number. We will discuss why bomb accuracy is so low. The function of bombers is to place a maximum number of bombs on target and get home safely. Factors which reduce bomb accuracy include heavy flak, fighter opposition, weather, and smoke screens. The factors which reduce target visibility required bombers to sight the aim point by radar, which is less accurate than target sighting by visual methods. In 5 of the 22 attacks, the target sighting method was visual. The target's aim point was sighted visually by the Norton bomb sight. This is the most accurate bombing method, as can be seen by the percentage of bombs striking within the target zone, which varied between 20 and 43%. This image shows ideal visual bombing conditions: no clouds, target debris, or plant smoke screens. The Germans deployed smoke screens rather than camouflage to mask the plant, given its size. Smoke screens were deployed on most of the later raids if needed. After September 1944, the plant was masked by 500 chemical smoke producers and 800 ovens. This composite image shows smoke screens during a raid. The plant's smoke screen during the November 25, 1944 raid, the plant smoke rising through the smoke screen, a US M2 smoke generator. The US M1 generator, the fog, traveled 5 miles downwind. B-17s encountering a smoke screen in this image, and in this image. Bombers were instructed to approach smoke screens traveling in the downstream direction like this. Bomb placement accuracy is strongly dependent on target visibility, as shown on this chart from a 1945 8th Air Force Tactical Development document. The x-axis is the distance from the aim point from 0 to 5 miles. The y-axis is the cumulative percentage of bombs that fell within this distance. With good target visibility, 85% of the bombs should fall within 1 mile of the aim point. This value drops to 60% if visibility is poor due to smoke screens, target debris from previous attacks, or cloud cover. This is an example of target debris from previous bomb group attacks. In all USAAF cases, the bombers released their bombs when the lead pathfinder released his bombs. The lead pathfinder's first bomb is a smoke bomb. The non-lead bombers replaced their bombardiers with toggleiers. In 9 of the 22 attacks, the target was sighted by PFF or Pathfinder Force. This is the least accurate target sighting method, with 0 to 14% of the bombs striking within the plant boundary. The target was sighted by H2X 3-centimeter radar, where just like visual releases, all planes in the group will release their bombs on cue from the lead Pathfinder's smoke bomb. An image of the H2X radar system. The target will be sighted by radar when it cannot be seen visually with the optical Norton bomb sight. The target may be obscured by clouds, smoke screens, and/or target debris from previous bombings. 6 to 48% of the bombs will strike within 1 mile of the aim point, depending on target visibility. In 3 of the 22 attacks, the target was sighted by a blended radar-assisted visual release with accuracy levels between pure visual and pure radar, from 6.4% to 23%. The British bombed at night with their pathfinders, dropping flare markers on the target for the remaining bombers to attack visually. Bomb plant placement varied between 4.3 and 14.7%. This page from a 1945 8th Air Force bombing report indicates that the striking force attacking a target masked by a smokescreen will need to be 4 to 5 times the size to match the number of bombs striking a non-smokescreen target. This is a similar visibility issue from smoke and debris from our own bombers. This table shows a reduction in bomb accuracy of the following groups from a 1947 USSBS bomb accuracy document. The reduced bomb accuracy levels expected is from the reduction in aim point visibility. The first group places 82% of the bombs within 1,000 feet of the aim point. The fifth group and on places only 30%. A decoy factory was erected, which diverted some 5.3%, or 4,550 of the bombs dropped during the first 8 attacks. In 7 attacks, more bombs fell on the decoy plant than the Leuna plant. Bomb accuracy circular error was found to be influenced by target type. Bombing is most accurate if the target is a coastal defense structure with a circular error of 900 feet, and the worst is synthetic oil plants at a 1,600-foot circular error. Of the 8,643 bombs that struck within the plant boundary, 1,387 were duds. That's an overall dud rate of 16.1%. The dud rate for the USAAF was 14.75% and 24% for the RAF. These images show collected unexploded US 500-pound general purpose and 4,000-pound RAF cookie bombs. The Leuna Works was one of the most protected targets in Germany, as discussed on this article from an April 2007 Air Force Journal article describing the Leuna bombing mission. It was protected by 1,700 heavy flak guns. This image shows the flak gun batteries of Leuna, flak over the target. Bomber crews considered the mission to Leuna as the most difficult and dangerous of the war. 128 bombers were lost over the 22 missions. Flak accounted for roughly 75% of these losses. Let's take a look at the 12th mission on November 2, 1944, where 27 B-17s were lost of the 574 attacking. The bombers dropped 2,591 500-pound and 5,409 250-pound general-purpose bombs at an altitude between 23,800 and 28,500 feet. Cloud cover was 10/10, therefore the target was sighted by the PFF radar. It is unknown if a smokescreen was deployed, but not likely since it was not needed isolated due to the cloud cover. The sad part of this attack is that of the 8,000 bombs dropped, only 6 struck within the plant boundary at the cost of 27 bombers. This chart summarizes the disposition of bombs dropped on synthetic fuel plants evaluated, not just Leuna. 84% of the bombs fell outside the plant boundary, 13% within the plant boundary, and 3 fell on decoy plants. 1.8% were duds, 7.6% in open terrain, 2.2% in vital areas, and 1.2% on pipes. So really, only 3.4% of the bombs dropped had the potential to cause damage. In summary, the reduction in bomb accuracy can be attributed to 1. PFF radar bombing needed to account for the low visibility conditions from weather, smoke screens, and bomb debris, 2. Decoy plants, and 3. Dealing with flak and fighters. This table lists the number and type of bombs dropped during the 22 missions. The significant columns are the bomb type, category, and weight class, bomb fusing from instantaneous to long delay, and number of bombs. Key points are 80% of the bombs dropped were the 500-pound or less weight class, with the 500-pound general purpose bomb is the most common. This page shows characteristics and a cutaway of the M64 500-pound general purpose bomb from a 1945 U.S. Navy bombs and fuses document. The weight equates to 525 pounds when filled with 267 pounds of TNT. The casing wall thickness is 0.3 inches. A B-17 or B-24 can carry 12 of these bombs internally. All of the higher weight 2,000-pound, 4,000-pound, 8,000-pound, and 12,000-pound bombs were all dropped by RAF Lancasters. The most common RAF large bomb is a 4,000-pound cookie bomb. This page shows sizes of the U.S. 100, 300, 500, 1,000, 2,000, and 4,000-pound general-purpose bombs. The level of destruction from these bombs detonating next to a housing complex, a 500-pound bomb, and a 4,000-pound bomb. B-17s have bomb bay room for up to 2 2,000-pound bombs. They can also carry 2 4,000-pound bombs, but they need to be mounted externally under the bomber's wings, like seen in these images supporting 2,000-pound bombs. The U.S. only deployed the 4,000-pound size general-purpose bombs by B-29s over Japan, not Europe. This image shows a level of destruction to a building struck by a 4,000-pound U.S. bomb. The sizes of various RAF bombs including the 1,000, 2,000, 4,000, and 12,000-pound bombs. This image shows a 4,000-pound British cookie bomb being loaded into a Lancaster, a 12,000-pound bomb. Characteristics and a cutaway of the 4,000-pound RAF cookie bomb are listed on this table from a 1948 British explosives document. The bomb's weight equates to 3,920 pounds when filled with 2,861 pounds of an explosive filler with a casing wall thickness of 0.31 inches. To protect the plant's vital equipment, bomb splinter protection layers were added to the vital tanks and gas holders. Concrete armor panels were added to the tanks for fragmentation and fire protection. This image shows the concrete blocks added to the storage tanks. They could be easily repaired. A blast-resistant wall added between distillation columns. These blast splinter walls offered no protection against the 4,000-pound RAF bombs. They offered some protection from near-miss 1,000-pound bombs and full protection against the 500-pound or smaller bombs. This image shows the damage from a 500-pound bomb direct hit on an 8-inch thick concrete arch. No damage occurred on the protected compressor or motor. A 1,000-pound bomb penetrated and detonated past a 12-inch thick concrete arch. The compressor was destroyed. The Leuna Plant Fire Department consisted of 3,100 fire wardens and 2,373 men. Only 10% of the building area was damaged by fire. The plant's fire department was responsible for damage containment. Water mains would break during the raids, but water tanks scattered throughout the plant provided firefighting water. The RAF longer attacks contributed to more plant fire damage than the shorter USAAF attacks. The gas generation plant was the most vital component of the Leuna plant. Only one-third of the time was it selected as the bomber's aim point. The smaller 500-pound bombs killed the plant by thousands of inefficient cuts. The smaller 500-pound bombs created breaks in the utilities, but these systems could be fixed quickly. They rarely destroyed the vital equipment. These bombs did little damage to the plant's major vital installations, but did accumulate into a large amount of minor systems damage. This overwhelmed the repair crews. 80% of the bombs that detonated inside the plant were at a weight of 500 pounds or less. These bombs broke water and sewer lines, power cables, and overhead piping. This damage could be repaired. This image shows plant piping damage. These bombs also damage buildings, but not the vital machinery within the building. The purpose of bombing is to prevent war production. The aerial attack should have resulted in permanent damage to the vital systems. The plant resumed production after the attacks. Much of the damage inflicted by the 22 attacks was superficial. Utilities damage from a 500-pound bomb. Thousands of these breaks stopped production temporarily. Cable damage from a 500-pound bomb. This can be repaired. This chart outlines the production output of the Leuna plant. The x-axis is a month and year. The y-axis is a production output from 0 to 110%. The vertical lines are the bombing events from 1 to 22. Production stopped for around 11 days after the first bombing mission and 72 days after mission 6. Only large bombs destroyed the plant's vital equipment. In a unanimous opinion that with proper bombing conditions, the higher weight 2,000 and 4,000-pound bombs were more effective than the lighter weight bombs. Most of the plant's damage was from bomb blast. This table summarizes the primary cause of damage at the Leuna plant. In order were blast at 56%, fragmentation 18.1%, fire 14.7%, debris 8.2%, and shock 3.3%. This image shows an accidental detonation of an RAF 4,000-pound bomb. This footage shows the blast of a U.S. 4,000-pound general-purpose bomb. This 4,000-pound bomb is statically suspended 20 feet above the ground and detonated by an electric blasting cap. At a slower speed, you can see the shock wave moving towards the camera. The detonation's intense white light lasts 0.003 seconds, and white hot steel casing fragments are projected outward at a speed of Mach 9.4. Yes, Mach 9.4. Tying the three bomb detonation event sequences, notice the bright light, casing fragments, and ground shock wave. The damage from a 4,000-pound bomb detonating 100 feet away from a pipe that collapsed. The results of 3 4,000-pound bombs and 8 1,000-pound bombs detonating in a building. All 7 machines were totally destroyed. A direct hit from a 4,000-pound bomb. A 4,000-pound bomb's near miss can also inflict damage. In one example, 5 500-pound bombs detonated 15 feet away from a gas holder. The gas holder shell was not damaged. A single 4,000-pound bomb struck 45 feet away from a gas holder. It was completely destroyed. Incendiaries were not used effectively. They were dropped too quickly. They should have been dropped a few minutes after the high explosive detonations. Most plant shutdowns were from damaged utilities. Gas pipes were penetrated by bomb splinters, which were repaired incorrectly. After startup, they leaked from the repaired line and exploded, sometimes causing more damage than the bombing. Only 105 of the 1,121 4,000-pound bombs dropped by the RAF actually struck the plant. Plant personnel called them air mines due to their destructive effect. The survey report estimated the number of 4,000-pound bombs needed to destroy the plant on this page. It takes 3 4,000-pound bombs to destroy the plant's vital components within each acre of the plant. The plant's vital gas generating system lies within 30 acres of the plant. Then 90 4,000-pound bombs would be needed to take the plant out of action. Assuming 10% of the bombs dropped will strike within this 30-acre area, then 900 4,000-pound bombs would be needed to fully stop the plant's production. This is 10% of the weight of the bombs actually dropped. This would likely need to be an RAF effort, as B-24s were not designed to carry 4,000-pound bombs, and B-17s can only carry them on external racks, where the drag would likely reduce its range below the distance needed. B-29s, on the other hand, can carry 4,000-pound bombs internally. It would have taken 225 B-29 sorties to disable the Leuna plant. The biggest takeaway from the 83-page damage study report is synthetic oil production would have been more affected by attacking the plant with 4,000-pound bombs. These attacks would target the 30-acre gas-generating system. Attacking the plant with 4,000-pound bombs is more effective than attacking the entire plant with smaller, ineffective 500-pound bombs. Fewer sorties would have been needed to accomplish plant shutdown with less bomber losses. This would have a major effect on the war if the approach was applied to the other 24 synthetic oil producing plants. This chart outlines Germany's synthetic oil output by month and year. The synthetic oil output once plant bombing started in May of 1944. If an effective bomb size was selected, this would have destroyed the plant's vital systems within a couple of months. This would have likely led to Germany's collapse much sooner and hence saved thousands of lives. Let's take a look at a video showing the post-war damage of the Leuna plant.
Battered to a shambles, the Leuna Synthetics plant at Merseburg, Germany, typifies destruction achieved in the Allied air effort to paralyze the Wehrmacht. Primary target for 8th Air Force heavies from May to December 1944, the Leuna plant was Germany's third largest producer of synthetic fuels, nitrates, alcohol, and ammonia. The plant's synthetic oil capacity alone was 600,000 tons a year, 10% of the total amount available to the Nazis. And its production of ammonia was the greatest in Europe, 1/3 of the entire enemy supply. The plant covered an area nearly as large as the whole town and employed 25,000 workers. The campaign against German oil, which began in May 1944, called for the destruction of 24 synthetic plants and 80 refineries. By August, Allied bombs had cut the enemy's fuel-making capacity by 63%. By April 1945, this plant had utterly collapsed, and the Nazis' ability to produce petroleum products had been reduced to 2.5% by continued Allied bombings. The attacks on synthetic oil works were the most effective of all strategic bombing and most decisive in Germany's defeat.